Welcome back, welcome back, welcome back. I'm Lisa Blackburn. This is my YouTube channel for everything I want to talk about science and math. Today we're in AP Chemistry learning about equilibrium. Okay, so this is considered one of the hardest topics, but I don't really think it's that bad. I think people are just totally overreacting. That it's got a little bit of fun math. Math is great. And it's got a little bit of like thinking where you have to sort of think about how things are going to change. And that's not too bad either. So it's like little puzzles, okay? So the first idea is that some reactions, and y'all remember RxNS is the abbreviation for reactions, some reactions are reversible, like rechargeable batteries. Every day your rechargeable batteries go forward, and one of the products of the chemical reaction is electricity. And then your phone is dead, and it has reached equilibrium. Nothing's happening. It's not going back or forth. The reaction is done. But then you plug it in and you start giving it more products, and that pushes it back to reactants and the chemicals reform. So this is something we're all really familiar with the power going out, with the storms over the weekend. Some of my devices reached equilibrium and could not have the reverse reaction happen. So another one is water. You can split water into hydrogen ions and hydroxide, or you can have hydrogen ions and hydroxide get together and make water. It goes back and forth both ways. When they stop going back and forth, and this is exactly what Maxwell said, that point is called equilibrium. And you write it, when you write those reactions, you write a double arrow, showing it goes both ways. So this is the definition. Chemical equilibrium is a dynamic, and that's an important word here. The reaction doesn't stop, but it reaches a point where there are products being made, but there's reactants being made at the same rate, and if you took the concentrations, they're remaining constant, okay? The reaction does not stop where the concentrations of all reactants and products remain constant, but they are not equal. It doesn't mean that they're all going to be equal, they're just the amounts are not going to change. The rates of the forward and reverse reactions are what's equal. They are equal. Okay. So here are some graphs. You know how AP loves the graphs. Here are some different graphs that represent it. Here you start off with your forward reaction and your reverse reaction, and when equilibrium is reached, they are equal. Another way to look at it is like the graphs we had last unit, where you start off with lots of reactants and no products, but then as it goes forward, you get more and more products and less reactants until these amounts stay constant. Notice they're not the same, but they stay constant. So there are like 4 ideas in chemistry that control everything. There's the idea of enthalpy and entropy, heat and disorder, and then there's energy, and then there's nature likes balance. So a lot of this, if you will get in your head, nature likes balance, it'll all make sense. It's all about balance. Okay, so that's 7.1. That was easy. 7.2, if the forward reaction is fast, and the reverse reaction is slow, then you will have more products than reactants at equilibrium and vice versa. So it's not that the amounts are the same, but and if it's really moving forward, you're going to get a lot of products. If it's not moving forward very much, you're going to have more reactants. So the next thing is reaction quotient and equilibrium constant. Okay, so in our learning target, I asked you about K and Q and what those stood for, and y'all were like, I don't know. Well, this is it, reaction quotient and equilibrium constant. So let me explain it to you. We're going to explain it to you before you look at it. Okay, so what we're going to do is we are going to write down a math formula based on our balanced chemical equation, and then sometimes that's all you have to do. And then sometimes they give you numbers to put in and you solve it. And this what you're solving for is telling you how much our equilibrium is going to completion. Some reactions are not reversible and they just go to completion. When I burned a match, there's no way to get that wood and back again, and the oxygen back, and that match is gone. That thing went to completion. But these reactions that reverse, we are going to get a number that is going to tell us how far they go to completion. Okay, got that? The big picture in your head? Good. Okay, so the math equation you're going to write is called the equilibrium expression. It is a math formula based on concentrations in the balanced chemical equation that shows how much a reaction goes to completion. The answer to the math problem is called the equilibrium constant, and it's a value, a number obtained by putting the concentrations into the math problem that tells you how far it goes. So this is how you write the math equation. If you have an equation where you're adding a plus b to get c plus d, and little a, little b, little c, little d are the coefficients from the balanced chemical equation, then how you do it is you write the products in the numerator and the reactants in the denominator raised to the power of their coefficient. Do y'all want me to say that again? The math problem is you take the products, what it makes, and you put them in square brackets, meaning the concentration, and you raise it to the power, to the number that is the number written in front when you balance the equation, the coefficients. And then the reactants, the ingredients, go in the denominator. And when I do this, I always write the numerator first, because you're going to find out later, sometimes it doesn't have a denominator. We'll talk about that later. So it just always, you end up writing the products first on top, raise them to the power of their balanced chemical equation, and then the reactants on bottom. So here's an example. And this is the reactant for ammonia. Remember, it's named after the Egyptian god Amun-Ra, and it's in Mr. Clean. That's what our drawings have to do. Okay, so I write the products first. The product is NH3, our ammonia. You write it in square brackets. Square brackets means concentration. You raise it to the power of the coefficient. That's not hard, is it? Does this seem familiar to those of you who had me for honors and you did it in honors? You're starting to remember? And now we do the denominator. So I'm going to put in the square bracket N2, and it only has a 1, so I don't write anything. And then in the square bracket, I write H2, and I raise it to the third power. Sometimes all they do is ask you to write that. And that's the whole problem. Write that. Okay, and then sometimes they'll give you numbers, they'll tell you what the concentrations are, and you substitute them into the square bracket, and you do the math. But sometimes they just want you to write the formula here. The expression, okay? So now, so this is called KEQ. Now, when you write this, you have to write KEQ equals. If you don't write that, it's wrong. You have to write the whole math, and that includes what it equals. So don't leave that part out. They will count it wrong on the AP test if you leave off your KEQ. Now, there are different types of KEQ. KEQ is the big umbrella term, the equilibrium constant. But that equilibrium constant can be based on concentrations like this one is, and sometimes instead of writing KEQ, they write KC, meaning it's based on concentrations. And if it can be based on concentrations, you've already figured out there's something else it could be based on too, right? So if it says KEQ or KC, either one, this is called the regular way, and it is based on concentrations. I already wrote all that, didn't I? Yep. Based on concentrations, okay? But there's another KEQ called KP. And instead of being based on concentration, it's based on pressures. The formula is exactly the same, but the symbolism is different, okay? Let's see, but you do it exactly the same, so that's easy. So now, this is, remember how I told you that sometimes there's no denominator? This is why. If one of the ingredients or the products, the reactants or the products, is a pure solid or a pure liquid, you leave it out. So notice how these were all gases. Gases go in. Aqueous goes in. But if it is a pure solid or a pure liquid, you leave it out. So these are not included. And we're going to see examples of that in our notes. Okay, are we ready to move on? This isn't too hard yet, is it? To be considered one of the hardest things in chemistry? It's not that hard. I think people just like get to this part in chemistry and they're tired. And they're like, I can't learn anymore. And then they reject it. So just don't reject it and you'll be fine. We are almost done. 7, 8, and 9 and we're done. And 8 is pH and I already taught you half of it in honors. Okay. So you don't put those in the math problem, the equilibrium expression. Sometimes you're given concentrations to calculate this, sometimes not. Sometimes you just write the equation. Sometimes you fill in the answer. So here's an example problem. Consider the reaction, and this is for making smog, which is part of pollution. This chemical is in smog and pollution. At a certain temperature, a mixture at equilibrium contains this concentration of N2O4 and this concentration of NO2. Calculate the equilibrium concentration, and when they put Kc, they could put KEQ, but they put Kc because these are concentrations. So first of all, we write our formula, okay? These are both gases, so they both go in, and I like to write products first, so I'm going to write it. I draw a square bracket, and I put NO2 raised to the second power. Where I got that second power from is that 2 right there in the balanced chemical equation. Now I write the other one. I draw a square bracket and I write N2O4, and it doesn't have a number in its balanced chemical equation, so I don't write it. Now I substitute the numbers they gave me into the equation. Now, I think it's better if you sing the song Substitute before you do it. You can do this without singing, but you won't have as much fun. Okay, so I'm going to write NO2, and they said that it was 0.4, so I'm going to draw my square bracket, 0.4, I can put 0.40, raised to the second power, and in the denominator at 0.2 raised to 1, but we don't write ones. And I got, for the answer, 0.80. Put a box around it. It's more fun with sound effects. Whoop, whoop, whoop. Notice, there's a constant, and it has no units. I like it when there's no units, because then there's no units for me to mess up. Okay, so it's just 0.8 is the answer. That's not hard, is it? So we did those in honors. You might not remember it, but we did. Okay, so here sometimes it's Kp. And remember I told you the formula is exactly the same, just the symbolism is different. Instead of writing square brackets, you use rounded brackets. And instead of just writing the chemical, you write, for the symbolism, you write P, and then as a subscript, the chemical, because it's the pressure of that chemical. But you still put products on top, reactants on bottom, and you still take it to the power of the balanced chemical equation coefficient. Okay? That's not hard, is it? Okay. So look, we've done section 1, 2, and 3 already. So section 4, calculating the equilibrium constant. Okay? When you do these problems, you have to remember to leave out the pure liquids and the pure solids. They'll try to be tricky with that. Also, they will give you a temperature in the problem, but it doesn't matter. You ignore it. You don't do anything with it. The reason why is temperature does affect equilibrium, but it doesn't matter. So just don't get confused. Don't do anything with that temperature number. Don't add, subtract, multiply, or divide. Just pretend like it's not there. It's just something to confuse you. All right, now we're to number 5. So sometimes you'll be asked questions about, well, what does this mean? You got a number, what does it mean? The magnitude, okay? So this is what it means. If your answer to the math problem, KEQ, is really large, bigger than 1, you have a lot of products, and the reaction goes toward completion toward the right. If it is really small and it is less than 1, then you have a lot of reactants that's not going very far to completion, and it stays to the left. And if you get in the habit of always writing K first, it makes an arrow and it tells you which way it goes. That's handy. Now, if you watch the Krug videos, he is going to have you do this opposite, and he uses Pac-Man as a symbol. I think it's easier to do it my way. Leave Pac-Man out of this and just get in the habit of always writing K first. And then the other thing you're going to have, the answer, or Q, we're going to get where there's Q. And if so, I'll just say, tell yourself, I write K first. You can watch Krug. If you like his way better, you can do it. I give you permission to do it his way, but this is my way. All right, 7.6. See, look how we're zipping along here. Okay. Properties of the equilibrium constant. Okay, so sometimes they'll make you do math on the answer to the problem. Okay, and this is what you do. I'm going to go over this, but this will make more sense when you're actually doing the problems and you have to do it. Then practicing will make sense, but this is where it will be in your notes. Okay, sometimes they will give you an equation, and then they'll write it the other way with the products first instead of the reactants, which is totally okay because these things are reversible. But if they do that, then KEQ will become the reciprocal. You flip it. It's 1 over KEQ. So that's something they can make you do. They can say, the KEQ of this is a certain number. What's the KEQ of this? You just do 1 over it. Okay. Next thing. Sometimes they'll want you to multiply the reaction by a factor. It's kind of like how we did with Hess's law. If you do that, then they'll say, now what's KEQ? What you do, you don't multiply like you did in Hess's law. Instead, you take KEQ to that power. Whatever you multiply it by, then that's going to be your exponent. Okay, and then the third one, sometimes you add the reactions together like we did with Hess's law. If you do that, you multiply the KEQs. If you have two different reactions and they want you to add them, you don't add the KEQs like we did in Hess's law, you multiply them instead. So just remember, this is here in your notes. When you get to the problem, flip back, you'll know how to do it, and the more you do it, the more you'll remember to do it. All right, 7.7 of 12. Look how fast we're going. Okay, this is considered a hard part of chemistry. I don't think it is. They're fun little math puzzles you get to solve. But when I was talking to another chemistry teacher here at the school, the other chemistry teachers are always saying, what are you doing in AP? Because like it's something they never get to teach because, you know, only AP teaches the college chemistry, so they don't get to do it. So there was another teacher, and he asked, what are we doing? And I said, oh, we're doing the ice tables. And he was like, oh, I hate the ice tables. And there's another thing that is Le Chatelier that we're going to talk about in this unit. And another chemistry teacher was like, oh, I hate Le Chatelier. But we're not going to hate on these ideas. They really are not bad. They're just fun little math puzzles that we get to solve. And math is a game that you can play and win. You can be good at math, get a college major that uses math, and get a lot of money. So that's a game you can really win. My son Eli right now, graduating with an engineering degree, 4 companies are competing over him. He has not even graduated yet. And they're offering and counter-offering, giving him more and more money. It's a game you can win. Math is the game. It's fun and profitable. Okay. So here, these are called sometimes they're called rice problems or icebox problems. So, how we're going to do this, make sure I'm at the right place. Okay. Sometimes they give us initial concentrations, and you have to solve for final concentrations with equilibrium. You organize the problem using an icebox. You know how when I have you do stoichiometry, I have you use the balanced chemical reaction as a table that tells you what order to do the problem in. This is the same sort of thing, and we're going to make a table with our chemical reaction that's going to tell us how to do the problem. And the table has a name, and they either call it rice box or icebox. Notice RICE or ICE. Some people leave off the word reaction and they just have ice. Other people write the word reaction and they have just ice. And a lot of times, like when you do this on the AP test, go ahead and write, like I wrote initial change equilibrium. You don't have to do that. You can just write ICE, and it will make your grader happy that you know what you're doing using an ice box, okay? So just write those little letters, ICE. So this is how you do your box. First, you write your balanced chemical equation. Then you write your initial concentrations of your chemicals. Then you write your change, and then you write what it's going to be at equilibrium. And you're going to have something you don't know, X, and you're going to solve for X, and then you're going to fill it back into your equation. That's how you do it. So let's see an example. Consider our smog reaction again, and we have the equilibrium constant, Kc, and that's given to us. There's a temperature. We don't care about the temperature. And then we have a concentration of this chemical, and we want the concentration, the final concentrations of them all. So step one, I write my balanced equation. Next, I write my initial concentrations. And I initially had 0.5 of that one. And initially, when it started, I had 0 of that one. Now, they don't bother to tell you that when it starts, you have 0, because that's just as logical, right? Okay, so 0 goes there. And then they changed. And this one lost some, and this one gained it. And how you know that that's X and that's 2X is from the balanced chemical equation. This went down by a certain amount, and that's going to go up 2 times that amount because of that 2 right there. Everybody see where I got that? That 2 came from your balanced chemical equation. So that one goes down by X, that one goes up, because that's our products, by 2X. Now I add them up. 0.5 plus negative X is 0.5 minus X, and 0 plus 2X is 2X. Everybody good so far? Okay, next, I write my equation, my expression, my math problem. So I put products on top, raised to its coefficient, reactants on bottom, raised to its coefficient, but it's a 1 and we don't write it. Then I substitute in for these concentrations my things here. I substitute that in and that in, okay? So I do products first, so I wrote 2X here, raised to the second power, and I wrote this in the denominator, and they told me what it equals. So now I have a math expression that I can solve for X, can't I? Now it's a little fancy, but I can do it. Okay, so let's do it together. So if I was going to solve for this, the first, you always have to start somewhere in a math problem. And I like to start with what's making it ugly. And what's making this ugly is it's a fraction. And we hate fractions, so I can unfractionify it by getting rid of the denominator. A denominator is just dividing, and you can get rid of it by multiplying, because you can do anything you want as long as you do it to both. The numerator and denominator are both sides of the equal. So I'm going to take this, and I'm going to multiply this by 0.5 minus X on this side, and I'm going to multiply it over here times 0.5 minus X on that side, and those mark out, and I'm left with this. Now I'm going to rewrite it, okay? So I've got 2X squared equals 0.21 times 0.5 minus X. Does everybody understand what I've done so far? Okay, so now the next one I'm going to get rid of the parentheses, because, you know, please, please, my dear Aunt Sally, parentheses are next on the get rid of things list. So I'm going to use the distributor property and distribute. Whoop, whoop. More fun with sound effects, right? So I've got 2X squared equals 0.105 minus 0.21x. That's a little hard to read. Can you see it? 0.21x. All I did was the distributive property. Now, what is making this ugly now? Oh, I left off my parentheses. Whoop, whoop. That'll make you get the wrong answer. All right, let's make it ugly now. the fact that this is going to have an x squared, isn't it? So let's go ahead. I should have simplified that there. I didn't. I'm going to fix it and simplify it. Hopefully that'll erase. Yep. Okay, now let's go back. Let's do what I should have done. This squared goes for the whole thing too. That's the distributive property too, isn't it? So this is 4x squared. Everybody understand how I did that? Ethan, are you with me? 4x squared. Okay, so what is making this ugly is that x squared. This is a quadratic equation now, isn't it? It's not ugly, it's fun. We get to do the quadratic equation. You remember Algebra 1? Sitting there going, when am I ever going to use this? Today's the day. Quadratic equation. Yay. All right, so I got to get it all on one side. Remember how the quadratic equation works? You got to set it all equal to 0. Remember that in math? So I'm going to subtract 4x squared by both sides, and I get 0 equals negative 4x squared. And then I should put my x's next. You know the math etiquette. You do your x's in descending order. So I'm going to do minus 0.21x. And then I've got plus, we're going to kind of go down this way with it because it's my little Iceman for the ice table is getting in the way. It's 0.105. Now, we are going to use our calculators to solve the quadratic equation. Evelyn last period said, can I just solve it myself without my calculator? No. When you're getting things like 0.105 and 0.21 in decimals and these problems, you must use a calculator that can do quadratic equation. If you've got the TI 8234, I will give you programs to solve it. Or else you're going to need the 36. It can solve it also. Somebody told me last period what you push. I don't remember. Second something you use for a quadratic equation under the 36. What is it? Polysolve. Second polysolve. That's it. All right. So everybody right now on your calculator that can solve a quadratic, this is your A, that's your B, and that's your C. So if you have my programs for the 84, you go to Program, where it says Program, and then the first program is A quad. Pick A quad, and it's going to ask for A, B, and C, and tell it -4, -0.21, and positive 0.105. And you should get, when you round it off, that, and there'll be two answers. You ignore the negative one. It can't be negative. You only take the positive one, and it's 0.14. Okay, so everybody try it and see if you get it. It'll round off to 0.14. Right, you ignore the negative one. The negative one's no good. The right answer is the positive root. You know, answers in quadratic are called roots. Yes, ma'am? You have programming that's not there, there's no A quad? Let me see. If you don't have it, my plan is to give it to you tomorrow as you come in. Oh, that's it. Okay, so now hit enter. You hit enter to make it go. Now put in A, B, and C. So hit A quad if you got it, and then do A, B, and C. B quad is nice because it will give you the vertex. So that one's real nice for math. And really there's a third quadratic program I give you called Discrimi, and it will give you imaginary answers too. Ooh, valuable, isn't it? The imaginary answer is given to you. Okay, so everybody got 0.14 if you round it off? We are not through with our math problem. Now we have to take this and substitute it back into those for x to get the values. And when I did that, I got 0.363 for the concentration of N2O4, and I got I didn't give myself room here, 274 for the value for the NO2. I try not to use the organic names with y'all.
So this
Yeah.
is to calculate the equilibrium.
These are the concentrations that this reaction has at equilibrium at that temperature. And that problem will be on the AP exam. And if you can do it, yay. It will be one of your free responses. Okay, that's not so bad, is it? I mean, I can just about guarantee that problem is going to be one of your free responses. You might have to balance it first and then write the expression and then substitute it in. And then they might have a few more questions for you. But this is one that they love. They love these problems. Okay, so how you do it. You use the quadratic equation, your calculator, ignore the negative answer, fill it back into the equilibrium for the answers. Sometimes you don't have to solve for x, you just solve it like a puzzle. Sometimes you don't use the quadratic equation, but you square root both sides. That's a verb, right? Square rooting, an action verb, you square root both sides. Sometimes they'll give you Kp instead of Kc or Keq, and you might have to use Dalton's law. Remember, Dalton's law is the total pressure is the little pressure is all added up. Krug has some good example problems. I would definitely, in my study time this week, watch the Krug videos at some point. If you're doing these problems and your Keq is very small, way smaller than 1 times 10 to the negative fifth, you can ignore the change and it makes your math better. Okay, so there is a way that you're supposed to do it, and then you check your work to see if you're allowed to ignore, to simplify your math using this trick or not. How I want you to do it is this way. I promise you it's the best. I want you to memorize that if the Keq they give you, this is going to be a given, is smaller than 1 times 10 to the negative fifth, then you can do the shortcut. We are not going to do the check. Now, Krug shows you how to do the check, but you will notice it takes him 4 or 5 minutes to do that. That's an eternity on the AP test. Instead, we're going to not do the check, and we're just going to memorize that if it is smaller than 1 times 10 to the negative fifth, we are allowed to do the shortcut. And I'm going to teach you the shortcut now. Okay, everybody got that? All right, so this is one. It says, what is the concentration of an equilibrium at, what is the concentration of equilibrium of a 0.15 molar solution of KCN, and our Kc that is given to us is 10 to the negative 10th. It's super small, smaller than 10 to the negative fifth, so we are allowed to do the shortcut. Okay? So this is what you do. You write your equation. That's the R for rice. We write our initial concentrations. So to start off, we had 0.5 of that and 0 of those because, you start off with 0. The change is this went down by a certain amount x, and when it went down, they went up. And these both have coefficients of 1, so they're just both plus x. If they had different coefficients, it would be that coefficient x. Now we add them together, and we get 0.15 minus x, and then x and x. And we fill them into our math equation. So it's x squared with 0.15 minus x. If we did this math, we would multiply both sides by this, and we would end up with x cubed. And that's harder than x squared, isn't it? So we want to take the shortcut and go faster. On the AP exam, it's all about fast. And we want to take the shortcut. And the shortcut is if that we get to ignore this little minus x thing because it's small, and we do that instead. Okay? So then we solve for it. So what we would do to solve for x, why is x not alone, is being squared and divide by 0.15. We're going to get rid of the fraction first because fractions are ugly. So I'll multiply both sides by 0.15. I'll multiply by 0.15. These cancel out. And now, how do I get x by itself when it's x squared? What's the opposite of x squared? Square rooting. That's a verb too, isn't it? So I'm going to square what you do to one side, you do to the other. You take the square root of both sides. And I got 8 times 10 to the negative 6. So that's what x equals. Now, this is the check that you check to see if it's less than 5%. You do 8 times 10 to the negative 6 divided by 0.15 times 100, and the answer is 0.006. Do you see how far, far below 5% that is? So it's absolutely allowed. Now, if they ask you to justify the fact that you took the shortcut, you can put it back in and show that it's less than 5%. But really, if it's 10 to the negative 5th, you can do the shortcut. See, usually you don't have to check if it's 1 times 10 to the negative 5th or smaller. All right, section 8. We are zipping through our 12 sections, aren't we? So section 8 is the drawings. You know, every unit we got to look at the drawings. Okay, so here we have some drawings. Notice it's all blue. Then it starts turning to white. And then at the end it's got blue and white, more white than blue. Okay, that's how you look at the drawings. And they might ask something like this. Describe the KEQ if this is at equilibrium in picture 5. Okay, so you could say if it's at number 5, do you see how you have a lot more products than you have reactants? A lot more white than blue. So you could say it is large because it is mostly products. That would be a good little answer to that one. They could also say these are gases and give you the total pressure, for example, 2 atmosphere, and ask you to get the mole fraction of the blue dots at equilibrium. Well, you count them, and there's 4 out of 12 are blue dots. And then you multiply it by 2 atmospheres, and you would say the mole fraction is 0.67 atmospheres. So that's another kind of problem they can give you with the pictures. That's not bad, is it? The dots. Okay, section number 9, Le Chatelier's principle. Le Chatelier's principle, he's French, that's why we got little French things decorating our notes today. Figured this out. When a change is imposed on a system in equilibrium, the position of the equilibrium shifts in a direction that tends to reduce the effect of the change. Now, that's all fancy, but what it's saying is nature likes balance, and if there's a change, it'll do the opposite to get back to balance again. That's sort of the summary. So let me show you how it works. Here we've got a reaction, A plus B makes C plus D, and it is reversible from our double arrow. If you added more to the products, so you are pushing more products into your beaker, it's going to shift and make more reactants. It will go toward the left. Okay, can you imagine that? Okay, think of it the other way. You are making cookies, and you want more cookies in your reaction. You're going to add more ingredients, and that's going to push out more cookies, isn't it? You see that? More ingredients makes more products, more cookies. Okay? So that's our first one. We're adding more products, and it's going to make more of it go back to reactants. That's what you do every night when you charge your phone. You add electricity, the product, and it makes more reactants. Okay? If a gas bubbles up, number 2. So now we're making gas bubbling up. C and D are being made, but they're going away. They're making a void. Now, nature abhors a vacuum. That means nature fills a void. If there's a void over here, it's going to start pushing it this way to fill in that hole. It's going to fill in that hole, and it will shift to the right. It'll make more products. Okay? The side that doesn't increase decreases. So when I have this gas bubbling off, and it pushes it toward the hole, then you're going to have less A and B because they're going to get pushed over into C and D. Can you imagine that too? See, this isn't hard. You just have to think. Okay, if it is a gas in a closed system, okay, so now this is in a beaker, and I've got a lid on it, and I squish it down. What happens is that it will go to the side with less moles. So you look at your balanced equation, and the one that has less moles is where it will go, because if there's less moles, that's like a hole, and it tries to fill the hole. Okay? So in a gas system, if the pressure increases, the shift will be to the side with less particles, fewer moles of gas. If it's a gas and the pressure decreases, it's a balloon that suddenly gets bigger, it'll do the opposite and go to the side with more particles. Okay? Now, if you add an inert gas like argon, it has no effect. That's a good little tricky question. If you add a catalyst, it has no effect. I think the only thing the inert gas could do is if it was a closed container, it could increase the pressure. So that might be a little bit tricky. But if it's not closed, no effect. And if it's a pure solid or liquid, remember we leave them out of the expression, so it has no effect. If it is exothermic, just think of heat as a product, and then you just do it like anytime you would add a product, and it would shift toward the reactants. Adding a product makes it shift toward the reactants. And if you remove it, it'll shift toward the products. If it's endothermic, heat is a reactant, so it will do the opposite. Just think of heat as a reactant or a product, and then it shifts just the way everything else does. Okay? If a reaction shifts right, sometimes they'll say, well, what does this mean? It means that the KEQ is increased. If it shifts toward the right, if it's shifting toward the products, KEQ increases. The bigger KEQ, the more the reaction goes to completion. All right. So now, remember in our opening, I asked you what's K and what's Q, and y'all said, I don't know. So I'm going to tell you what it is before you look at the fancy words. Okay, so what it is K tells us what the concentrations of everything is at equilibrium. Sometimes they will give you concentrations and you don't know if it's at equilibrium or not. When you first pour it in, it's not at equilibrium. It takes a minute for it to all get evened out. So they will give you the concentrations and you don't know if it's at equilibrium or not, and you solve for Q. It's not K because it's not equilibrium. You solve for something else called Q. And then we compare Q to K, and we decide, is it at equilibrium? If they're equal, it's at equilibrium. Or is it going to the right or to the left? Okay, so that's what Q is. Is concentrations taken? We don't know if it's at equilibrium. We're going to figure out if it's there or if it's going to the right or to the left. Okay, so this is it. Q is the reaction quotient, Q for quotient. It's a ratio that reflects the concentration before equilibrium is reached. Sometimes they'll be tricky and give it to you where it equals it, but usually it's before equilibrium is reached. And what makes it great is it is the same exact formula as KEQ. We only got one formula. That's great, isn't it? So sometimes you calculate this too. So it's the same exact formula. Instead of a K, we now have the letter Q, but it is the products over the reactants raised to the coefficients. Now, why do you do this? If you know KEQ, that'll be given, and you solve for Q, you can know which way it's going. And how I do it is I always write my KEQ first, then Q, and then I put my greater than, less than symbol, and it will tell me if the reaction is going to the right or to the left. If KEQ is greater than Q, then it makes an arrow going this way, and it will shift to the right. If KEQ is less than, it makes an arrow going that way, and it will go to the left. The greater than or less than makes an arrow. And I think that's the best way to do it. You just got to remember to write KEQ first, and then write your greater than, less than symbol. Craig does the opposite, and he uses Pac-Man. If you don't like this way, you can go watch his way, but I'm not going to tell it to you because it will confuse you. I only teach you one way to do it, my way. But Craig, Pac-Man is cute. I do love a Pac-Man. So I was a little tempted to change my way, but I was like, no, my way works. Kids have learned it right for years. We're sticking with my way. All right, so sometimes they'll give you K, Q, and Q. Sometimes you have to solve for Q. Sometimes they'll give you concentrations first. So it just depends. All right, next idea, number 11. And I'm going to make you do the same worksheet you did in the honors for that Q thing. Because those of you who didn't have me haven't done the worksheet, and those who had me have forgotten because y'all didn't know what K and Q were. So I'm going to make you do that honors worksheet to practice this. I think it's once you do that worksheet, you are golden on this. You are going to be so good at the math. The only thing you'll have to learn after that is those ice tables. Okay, introduction to solubility equilibria. This combines the ideas we learned about NAGSAG and solutions in equilibrium. A saturated solution, you know, where there's like can't absorb anymore, is at equilibrium. Even the things we learned were insoluble with NAGSAG can sometimes dissolve a tiny amount, and they will make you do a problem with this. And we can calculate the equilibrium constant for it, but instead of calling it KEQ or KC or KP or Q, it's the same exact thing, but now we are calling it KSP for solubility product constant. So that means we're figuring out the K when it's only a little bit soluble. Okay, everybody good with that? These are actually a tiny bit easier. I'll show you why. Okay, so here's an example. What is the molar solubility of silver chloride in pure water given that its KSP is 1.8 times 10 to the negative 10? Now, you're thinking, no, I learned with NAGSAG, PMS, and Castro-Bear that silver chloride is not soluble. But it turns out it is a tiny little bit, and we can figure it out. Okay, so that's what this is. So here we've got our silver chloride solid. Just a little bit, ions are becoming silver and chloride. So we can write its formula, but notice this is a pure solid. So we leave it out, and it has no denominator. Remember I told you sometimes there's no denominator, so I always do the numerator first, which is the products. This is it. So you leave that out, no denominator, concentration of silver, concentration of chloride, and they give you the answer here. So there's the answer. But we are going to figure out what these are, what these numbers are with our ice table. Okay. So notice there's nothing here for the products. Normally you got for that. That silver chloride is a solid. We leave it out of our table. So we just have our initial, which is 0 for both of those. Initial for the products is 0. The change, I could have said plus X for both, but a lot of times they'll use S for solubility. So plus S's, you add them up, 0 plus S is S. Now we can write our expression. Our KSP is S times S, which is S squared, and we were given what it equals. So how do we get S by itself? By doing the opposite of squared, which is square rooting, and what you do to one side, you do to the other, and we can solve it. See how this is really easier than the other one? It has no denominator. You don't have to worry about ignoring part of the denominator. It's 1.34 times 10 to the negative 5th is X. And that was the concentration of those. So the molar solubility of silver chloride in pure water, the concentrations are those. Not very much, 10 to the negative 5th. Tiny, tiny amount, yes.
So since it's being put in a tiny amount.
You gotta talk louder, what?
Since it's only being put in as a tiny amount, it's fair to assume that the molarity is going to be tiny as well?
Yes,
Okay.
yes. Did y'all hear Maxwell's question? He said that this KSP was so small, 10 to the negative 10th, that you could kind of know that this amount of this molarity was going to be really, really small. And as you see, it is. And we know that because not much is dissolving. So that's good thinking it through, Maxwell. Okay. Sometimes they'll give you grams per liter that can dissolve and ask for the molar solubility, moles per liter, and you have to use the molar mass and convert. Sometimes they just want regular solubility, Kc in grams per liter. Sometimes they'll give you concentration, and you use the coefficients from the balanced chemical equation to multiply and get the other concentrations, and then put it in the formula and solve for KSP. Sometimes you're given 2 KSPs, and they're asked which dissolves more. Let me find this. And it is the one with the bigger value. Bigger K means more is getting dissolved. It's going more toward the products. More is getting dissolved. So we'll do example problems with this. For this week, I want you to do 3 I do, we do's per day. So today I want you to do 1 through 3, Tuesday, 4, 5, 6, Wednesday, and so we'll get them all done this week, and then we'll have time to just practice and study for our test on Tuesday. I don't want you trying to do all of these, Monday night. You're not going to do good on the test if you do that. Okay, so here's another problem. And they tell us the molar solubility for magnesium fluoride is this number. They want us to first write the net ionic equation, then figure out the math equation, then solve it, okay? So if magnesium fluoride, we should know how to write magnesium. Looking over there, remember, is +2. Fluoride is -1. Crisscross applesauce, you get MgF2. It's dissolving into magnesium ions and fluoride ions. You balance it with the 2 right there. Everybody know how to do that? Good. Next, we write our formula. There is no denominator. It's a solid. So we do our numerator raised to the power of 2 for that one. No raised for that one. Now we're going to, say our concentrations are what is lost here goes there. So these are adding that. This would actually be minus that. You get, this is going to be 2x because of that 2. This goes down by 1 mole. This goes up by a mole because it's a 1. This will go up by 2 moles because of that 2. This doesn't matter because it's a solid. But we have the answer to this. We know what the KSP is. It was given to us, 1.6 times 10 to the negative 11. And this is the numerator, x times 2x squared. There is no denominator. Now I can solve for x, can I? This is just a little algebra problem, okay? Now it is a little extra tricky because when you multiply, you get 4x cubed. So why is x all alone? It's got a 4 and a cubed. I get rid of the 4 first, divide both sides by 4, and I get 1.29 times 10 to the negative 11th equals x cubed. How do I solve for x cubed? How do you what's the opposite of cubing? Cubed rooting. So I take the cubed root of both sides and solve for x. Now how do you do that? On your calculator. If you have the TI 84, 83, 82, push the math button. I say that's the ironic button because they're all math. And look at number 4, and that's cubed root. So everybody right now on your calculator, see if you can take this cubed root and get the answer. Where am I? Doop, 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 doop. I got 2.35 times 10 to the negative 4. See if y'all can get that on your calculators. You getting it? See, isn't this fun? You're getting to do smart people things. Take cubed roots and use quadratic programs. School's boring for you smart kids. You're getting to learn something new. It's not boring. Okay, so here's an example that puts a lot of things that we've learned together. If 100 milliliter of 0.25 molar sodium chloride is added to 200 milliliters of 0.2 molar lead nitrate with a KSP of lead chloride is 1.7 times 10 to the negative 5th, will a precipitate form? So this is a Q versus KSP problem. And first of all, we need the concentrations. We have the concentrations of each chemical, but we don't have their concentration in the whole thing once we mix them together. So what you have to do is you have to take their molarity. Well, for first one, you need to get its concentration for the whole thing. So you take its molarity and you multiply it by its how much you started with it of liters, and that will mark out liters, because remember, big M is moles per liter, and if you multiply them, you've got 1 in the numerator, 1 liter in the numerator, 1 in the denominator, they cancel out, and you're left with moles. So step 1, multiply its molarity times its volume, and you will get moles of each one, okay? Then you need to take these moles and divide by the total volume, which is you add the two volumes together. And 100 plus 200 is 300 milliliters, which is 0.3 liters. So we're going to take our moles, 0.04 moles, divide them by our liters, 0.3, and we can get the concentration of the lead in our new mixed together solution as 0.13 molarity. Then we do the same thing for chloride, multiply the molarity times the liters, get the moles, add up all the volume, it's still 300, divide 0.025 by 0.3 liters, and it is 0.0833. Okay? Now we have concentrations, and we're going to put it into the Q expression. So here's our formula. Our lead chloride, lead and chloride, no denominator, it's a solid, just numerators, and then we substitute the values we just got in for them, and the answer is 9.2 times 10 to the negative fourth. Then we got to compare it to KEQ. We write the KSP they gave us first. This is usually a given. The K is usually a given. We write what we solve for Q second. We draw our greater than, less than symbol, and it's going that way toward the solid, toward the product, so a precipitant will form. How do we feel about that? Once you practice it, maybe you can do it. Okay. Sometimes they'll give you a reaction where there are two precipitants, and they'll ask which one will form first, and it's the one with the KSP that's smaller. That's the answer to that problem. It's the one that's smaller. Okay, last section. And this one's easy. Don't worry, this is getting a little easier, not harder. This is the common ion effect. Sometimes you are not dissolving in pure water, but something that has an ion in it already, like tap water, what effect does it have? Or they'll add another ion that is the same ion that's in our problem. It's called the common ion effect. Okay, so here I've got calcium sulfate breaking into calcium and sulfate. And they add some sodium sulfate. So we are adding some sulfate ions. Does everybody understand that? Can you see it? You got calcium sulfate breaking into calcium and sulfate. And we're adding more sulfate ions. Okay, according to Le Chatelier, if you add more products, what's going to happen? It's going to go that way, right? You push here, it goes over there. So that means we're going to get more solid precipitating out. Can you see that? If you can see that, then you understand this whole thing. You've learned it all. Okay, so let's look at it in here. So this is an example of Le Chatelier. So we added some more, we got some more ions in there. So that might mean it's going to go to the left toward the reactants, and more calcium sulfate will precipitate out because remember it was a solid. Ta-da! One of the hardest parts of chemistry, and you kind of understand it now. And once you practice it, I'm sure you'll do great. All right. Science is great.